What you see in front of me is a schematic diagram. This is taken from a book called Gabor's Data Analysis, and it actually shows how the entire data set has been split into the original data. That's the original data, and also have the live data. Now, the original data is actually the one which has been split into work set and holdout set. Now, this is the interesting thing. Now, usually what happens is you only have something called a train test split when you're carrying out modeling. This is very much a machine learning parlance, and just follow along if you are not aware. I'll try to explain as much as possible. So you'll see that once we actually come to this section here under work set, the model selection is followed by the creation of the training and the test sets. Now, you actually build the models on the training sets, then you evaluate the models on the corresponding test sets, and then you choose the model with the lowest average test set MSE. So this, of course, is talking about multiple models. In some cases, it can be a single model as well. But in this case, we are going to test out multiple models, and I'm going to explain what I really mean by that. So in one piece of code, we'll have multiple models, and we'll have multiple kinds of training test splits. So this is usually what is done, and that is pretty much it. And then you have the final prediction. But in this case, what we are also suggesting, and this is again a very well established, robust method for actually evaluating the performance and the accuracy level of your model, is what's called the split between the work set and the holdout set. So if you have a work set and then you have a holdout set, so in the holdout set, you'll have that once the model is estimated, you are doing the evaluation on it, and the using the estimated model, which is the best model from the previous stage, you're going to actually estimate you're going to evaluate it rather on the holdout set. So the holdout set is nothing but just like the train test split, which is working within the work set. So it's actually happening on the original data itself, that all of that train test split and then your model building, evaluation, and final prediction, all of that is actually happening within one section, which is presumably say 80% of the original data set, which is called the work set. And then you also have a completely untouched data which the models have not seen previously. That is your holdout set. So that again can be your 20%. So that is how we can actually properly, systematically carry out evaluation of your model, and therefore it is a more scientific and robust method. Now, if I actually drill down a little bit further, what I really mean, so this is what is really going on uh, within the work set. So you're building models on the training set. So your model is going to be split between training and test, and within the training set is basically the training is going on, and then the test is like 20%, you can see, and it is the test where you're evaluating in each of these cases. Now, what are these different cases? Set 1, set 2 to set 5. These are the different folds. These are the different um, instances of what is called a cross-fold validation. So that is where you create multiple versions of the same data set, which is the same. This is all from the same working set, as you can see. This is all within the work set itself, but you're creating different splits between training and test, so that you have multiple evaluations, not just one, and you then take the average of these to find out the best version. Now, the interesting thing here in this case is that we are not just doing multiple folds on the same model using the same model, but we have multiple models as well. So essentially we have multiple folds and multiple models. So suppose you have say 5 folds, that's been decided, right? So that's cross-fold validation. There's a method called k-fold, and k is 5 here, and you see that model 1, model 2 to model k. Now this is where k actually becomes 5 in our example. You'll just see, so we'll have 5, or rather 4. We'll have 4 models. All of them will be linear regression models, and will simply be progressively adding more predictors in the models. So that is how they will be differing from one another. And we will see that that there is a lot to discuss, of course, when it comes to accuracy metrics. Will be obviously once we evaluate the models on the training on the test sets rather for each of these folds, we'll see that the R squared, the MSE, the RMSE, all of these things are varying. And when you add predictors, in most cases you will get the R squared to be, we'll see the R squared is always increasing. Now in our case, of course, model k will be k equal to 4, so we'll have 4 models, 5 sets, so we'll have to actually have 20 different iterations going on in order to give you a better understanding of how well the work set is doing, to actually evaluate and estimate the model during the working set activity. After that is done, and after the average has been obtained to understand what's the best model, we will be using that on the holdout set. So this is the overall understanding. This MSE is nothing but your mean square error. This is your error or accuracy metric. And you basically get the average of these and you choose the one with the lowest MSE. This can be RMSE, this can be other error metrics. This is just a representation. Once again, this is from Gabor's book. The entire image has been taken from there. So I've used that concept and I'm summarizing it here, that you have linear regression, which is trained 5 times per feature set, once for each fold, and you get 5 MSE scores per feature set. As you can see, feature set is nothing but the model in this case. Don't confuse it with this sets here. This set is nothing but the K fold, which is the cross validation. And then you have the average to get a cross-validated performance metric, which is a single metric. The total number of runs, therefore, is 4 feature sets into 5 folds, which is 20 model fits during our total validation exercise. So this is now the code. I'm not going to go through the entire part of it, but what it really does is it first imports some important packages, as you can see, regression related, trend test split, k-fold, as I was saying, this, the metrics, and then you have the scaling part of it. And then you basically, what I'm doing here is, in this example I'm showing you, is I'm generating a synthetic data set. So the data set is not from real world data, but it's a synthetic data set, but it's been created in a certain way. And let me actually walk you through what the process is. So first of all, we have coefficients. We define the coefficients for the different media spends. So you'll see that there's a there's 2 as a coefficient for Google. There's 1.8 for Meta, 1.5 for TikTok, and then we also have a promotional discount as a sort of you can say a confounding variable or a additional covariate. So this is a control variable, and you see the coefficient of that is the highest. This is actually going to be interesting when we see just in a moment. And now we actually have, after the coefficients, we have also introduced a noise element, as you can see. So it varies between 0 to 3000, and that is simply given by the and the number of noise inputs is given by the number of samples. So we have 500 data points in our data set, and this is the data frame that we're going to be using. The data is the data for data spend, which is given by this, which is again generated using random numbers, and once that's been done, they have also been multiplied by the coefficient. So we actually know the true coefficients from here. And the best part about it is that once you know the coefficients in the data generating process, this is becoming very, very important, especially when you're talking about things like causal inference, when you have to understand in modeling that if you are able to generate a good model, it should be able to recover the parameters. So this is what is called parameter recovery, and it's an extremely important part of sound model building. So now you actually split it into your work and holdout sets, and you can see that the entire thing has been split into 80%, 20%, the latter being for the test, and rather that being for the holdout set. So again, the concept, like I said, the trend test split is the same concept, which we'll use again in a moment. And then we have then we are scaling the features. Scaling is important. We are basically saying that it's going to have all of the features are going to be reduced to similar sort of ranges. So 0 as mean and 1 as standard deviation. So that kind of alters it, but it also makes them very comparable. In case they have very different scales, something is in hundreds, something is in tens, something is in thousands, they are really apples versus oranges. So you can't really compare them, and any kind of analysis will be misleading. So that's why we scale the features. And then what we do is called cross validation. So we do a k-fold cross validation, n splits 5, we have 5-fold cross validation, shuffle through, and then a random step 42, just to confirm that the split that's going to happen actually remains the same every time this code is run. Otherwise it will just remain random. And then we so yeah, and then we have for features in feature sets, this is another loop that we are running. So for each feature we are going to have this trend test split. We actually saw that here. Feature sets again is the model. So for all of these models we are running through this loop. And once that loop is completed, we are basically carrying out the trend test split, as you can see, and then we are fitting it on the linear regression, and then we are predicting on the X test. So this is the version. So we are predicting on the test part of each of each set. And remember, we also have 5 folds. So for and this is going to happen for each of the folds as well. So for each model, and within that, as you can see, so there is a hierarchy here. So within each model there's also the fold as well. So 5 into 4, therefore 20 iterations. This outer loop is going to run 20 times, because the inner loop is also going to run 5 times. So this entire thing, therefore, ultimately gives us an average MSE, which, and we'll be choosing the lowest MSE version of it. And then so the CV results, the cross validation results, all of the results, by the way, right at this moment, not the best has been chosen, has been stored in features and MSE, average MSE. So what the features are and what the average MSE is corresponding to each model. And then we actually have a per fold metric for each model. This is where we are going to get an output, how the different metrics like accuracy metrics like R squared, and error metrics like say MSE, how these look like for each fold and for each model, for each feature set. So we actually need that, and we're going to get that in a tabular version out of as an outcome of running this part of the code. So once that's been done, then comes the selection of the best model, and that's where we simply take lambda xx1, which means that we're taking we are taking basically the best model, and that's basically taking the CV results, and that I think is the RMSE. Yeah, that's the MSE, because if you look at how this was defined earlier, we had the MSE and the features. So within that, now we are basically taking the different features, and the best features and the best CV are taken from CV result 0, because once it has been sorted, we are going to basically get the best model. So the lowest MSE, the best model is the one with the lowest average MSE. So once that's been done, you have the best model, which is once again fit into with the linear regression, and we now applied it to the work set. Okay, and we also applied it to the holdout set as well. Now we do this, we also do the training on all the models and evaluate on the entire work set this time. So this is coming from this part of the diagram. Remember, we're done with evaluating the different models. Now is our part to actually do the final estimation, the final prediction, using the entire work set. This time we're not going to have the trend tests, but we're not going to have just these different folds. No longer the folds will be there. This is now going to be a case of the entire work set being used for the final prediction. Once that's done, we'll move on now to the holdout part. So now, after the model has been chosen, we're going to use the best model, for actually doing the holdout prediction. So in this case, you'll see that we have actually done the holdout prediction for all the models, not just the best model, just to get a comparative picture. So once that's been done, nothing, as you can see, all of this is just calculating the different values, R squared, MSE, RMSE, for each of the models on the holdout set. So the holdout set is, again, remember, is that other part of the data set which the model hasn't seen, and therefore it is truly unadulterated, and the model has no idea what the data set is going to look like. So it's proper evaluation of your model. So now you combine your data set again, and then you this combination simply means that you are trying to understand how actual and predicted move together, just to get a comparative picture of how good the prediction was. And then you print a summary of the model, its different features, and then the different factors here on the work set as well as on the holdout set. Then you have the actual versus predicted plots. I'm not getting into the plots, simple plotting code, just to make it easy. And then you have the residual plots, which gives you the errors as well, what the different distribution of the errors. And then you have ridge and lasso regression, which is which is just going to give you an understanding of how, if you are carrying out standardization, how that or rather, I'm sorry, if you carry out L1 and L2 regularization, as they're also called, how that actually helps you if that actually helps you improve the performance of the model. So I'm not going to go into the detail of regularization here, but my whole point here is to show you how this entire thing has been brought together, how the actual data set has been split into a holdout, has been split into another part, which is of course your actual work set. So you see here the pre-fold test metrics. This is what I was saying, per fold, sorry. And so we have 20, right? So remember, that's what we said earlier as well. So 1 2 3 4 5, and it starts again. So there's basically 20 iterations starting from 0 to 19. So 20 runs of the models, and there's each of the model has gone through each of the folds, 5 folds. So you have test size of 80, you have the different R squared, different MSE and RMSE. RMSE is nothing but the root of mean square error. And you'll see that as we move towards the final model, which is model 4, you'll see that the R squares actually tend to improve and the MSEs tend to decrease, right, to a certain extent. See, the MSE has become to the power, this is 10 to the power of 6, this was 10 to the power of 7, right? So it's actually decreasing. As you can see, even in RMSE, it's easier to see. You'll see that this was close to 6,000. Then in model 2 it came around 4,000, and then finally in model 4, in 3 it became 2,800, and yeah, so it's basically decreasing, as you can see. So obviously in the different folds there are slightly different values, but ultimately it's the average that will be taken out of these values. So this is just to give you that understanding. This was for all the models. Now you have the best model features. So what among these different features? So remember, each of the model is taking out, as I said at the start, certain um, uh, features. So not all the models are taking all the features. So we had, as you can see, so these are the feature sets. So the first one had only Google, the second one had Google and Meta, the third one had Google, Meta, and TikTok, and then you had Google, Meta, TikTok, as well as promotion discount. So the final one, I think that's the one which is the lowest RMSE and the highest R squared. So that's, in this case, that's the case, because that's how it has been designed, right? I mean, we have designed the data set, we know that's the case, and that's what's coming out as well, even on the holdout. So therefore the model is actually working. So that the model is working well actually is determined by how well the holdout is doing. And you'll see model features, feature importances. So the first one obviously had only one feature. So what these bar graphs are giving you, by the way, is simply how well, what features rather within each model are more important. So the model 2 has 2 features, and you see spend of Google is more important. And this is, by the way, post scaling. This is not on raw data. So you already have done that standardization. Remember I just said where you're sort of transforming the data so that the mean is 0 and the standard deviation is 1. So this is and I think I'll probably also do a separate video on this and just show you what I am talking about. It's very interesting that if you look at the feature importances here, and if you look at the fourth one, it will be more clear that the spend Google is actually coming out with the most important feature, which is very interesting given the fact that if you look at the coefficients, the way the coefficients were set, if I can actually find that, yeah, there you go, the true coefficients. The highest true coefficient was actually for the fourth, the last one was promotion, right? But the thing is that this had the least spread. Okay, so the standard deviation was the least. Now what happens is it's transformed using standard scaler. Ultimately what happens is the standard deviation, which becomes a very important factor, and if your standard deviation is on the lower side, its importance, its relative importance is actually going to decrease. That's why you're in the feature importance bar charts here, even though the actual coefficient value was lesser for the true raw values, the transform values of coefficients actually became just the opposite. Google became higher just because the standard deviation was more there. So it explains more variance. Basically, that's the whole importance. That's the whole point of this feature importance analysis. More variance in the data set. And the model evaluation summary gives us for all the models. Remember, we didn't just do the holdout set only for the best model, although that's usually the best practice. This is just to show you a comparative analysis. And this is, as you can see, this is a continuation of the table in the second row here. So for the first model, the work set R squared was 0.5, and the holdout R squared was 0.4 or 0.47. And that is expected, right? There's going to be some drop in the holdout. This is new data, that it has not seen before. And then you have model 2, which is 0.77 in the work set, and 0.76 in the R squared, sorry, in the holdout. And then you have model 3, which is 0.86 and 0.86 again, very similar. For model 4 again, very similar. But the thing is, it's the model 4 ultimately which is the best, because it's also the RMSE, which is important. And you'll see that the work RMSE is actually the least in this case. The holdout RMSE is actually a little more for the fourth model, so that's interesting. So anyway, I mean, the point here is, which actually has the better R squared. So we have, as you can see, we have a slightly lower holdout R squared and a slightly higher work set R squared for the fourth model. So model 3 and 4 are moving very close together. So, but yeah, for some, but overall, we saw that the best model features, taking the average of the different numbers, we saw that this is the one which is the best holdout R square and best RMSE, the fourth model. There you go. This is the number that's been given here, 3092, and then you have 0.858, which is the holdout R square, which is this one. So the fourth model is still the best model, even though it's very close to the third model. There's only one best, right? There's only one king in the jungle. So this is the different plots now between actual and predicted, and this is for work set, this is for holdout set. For all the models, you'll have work set and holdout set. And finally, you have, as you can see, this is again, the data set has been generated in a way which is fairly linear, right? Remember, it's a fairly linear data set, and therefore the points, as you can see, are sort of moving always upwards, and therefore and the actual versus predicted is a very linear relationship. And you'll always see that for the holdout, it's sparse data, right? I mean, there are far lesser points, and that's expected, because in the holdout set you have far lesser observations. It's only 20% of the original data set. So the best fit is for the fourth model, by the way. This is the one which is the best fit. As you can see, very closely packed towards around the red line, which actually represents the true data, or rather, sorry, the predicted data, and the true data points are the blue ones. And this is the residual distribution, as you can see, fairly normal. The actual versus predicted, the work versus holdout. So this is the error, basically the residuals of the errors on the work set and the holdout set. And you would typically want it to be as normally distributed as possible, as few outliers as possible. So this is the best model, as you can see, very closely following the patterns of work and holdout, and very similar patterns, less outliers here. As you can see, that the bars here follow very closely a normal distribution, much better than the previous ones. So that's another reason why this is the best model. Very closely, basically they're centered around 0. That's the whole point. That's what a normal distribution really is. So most of the error bars are centered around 0. And so now comes those couple of bars for ridge and lasso regression. This is what shows you, after that L1 and L2 regularization has been done, what actually the R squared and the RMSE values look like. And again, once again, the feature importances, as you can see, it remains pretty much the same. It's the inverse of what we saw with the true coefficients, right? We saw discount percentage as having the highest coefficient, but in case of the post scaling, the post standardization thing, we saw the feature we see that the feature importance is kind of reversed, right? It's the discount which is actually the least one, and Google, Meta, and TikTok are in a descending order, and they are the most important features. And the RMSE and R square are actually not very different as well in this case, because of the very nature of the data set. But it's important to do these things as well. Sometimes, though, this is just done as an ad hoc basis, and this is only on the fourth model, by the way. But you can always do this. You can sort of build it right into the model itself if you think that these regularization methods are actually crucial. So the whole point of regularization, like lasso and ridge regression, L1 and L2 regularization as they're called, is to actually prevent overfitting. So your model should not only do well on seen data and not do well on unseen data. So that doesn't make sense, right? That's a really bad model. So in this case, what we have really done is we've worked with a data set where this actually naturally is taking place, and therefore lasso and ridge aren't necessarily doing anything better. They're not able to shrink coefficients or do other things that will improve the performance, and that's why you see very similar R squared and MSE values. So just to prove that, establish or demonstrate that point that I was making, why even features with high coefficients, high true coefficients, actually ended up being less important features by the feature importance analysis, is because of the standard deviation. So see here, the promotion discount percentage, the standard deviation is only 8.7, and for Google, Meta, and TikTok, these are very high standard deviations. Okay, so those are the standard deviations are much higher. The variance is higher. Therefore, they're able to explain more variance in the actual data set in the model. So so yeah, this is the whole model building process. But also more importantly, perhaps, um, is the fact that this shows how to do properly in a scientific and robust manner the prediction and the evaluation on the whole outset. So you want to not just build models, but actually build models which are useful, and they are useful only if they are actually evaluated properly. All right, otherwise you don't know if they're good models. And then the final step, of course, is to work live data, right? So this is live prediction. This is data you don't have anyway. You can't do anything about it, and then just hope for the best. That's what's written here, absolutely correctly. But if you've done the other part of the process correctly, then you have a good model. So this video was not just aimed at people who understand all of this in a very technical way, but also to give an overall understanding to marketers who are becoming more and more interested in things like modeling and marketing mix modeling in particular, and predictive analytics, and customer analytics, segmentation, and so many other things, and A/B testing, geo testing, geo experiments, and incrementality testing. They are having to sort of grapple with a lot of code and technical stuff, even if they're not doing it themselves. But if they work with a measurement expert like me, they actually have to understand really what is really going on under the hood, at least from a very holistic perspective. So that's what I've tried to provide here, and just to show you that modeling is not easy, but yeah, you can at least understand when someone is doing a good job with modeling and when they're not. You know what robustness in modeling actually means now, hopefully after the end of this video. If you have any further questions, please feel free to ask. Always happy to help and answer your questions. Do leave them in the comments below. Thanks for watching, and I'll see you in the next video.